Hey, everybody.
Hello.
How you guys doing?
Good.
I'm
How about you?
I'm doing really well, thank you. Just
Happy
found
Cinco de Mayo.
Young, you put your camera on without me giving you a hard time. Woohoo! Just you and I. Everyone else has got their cameras off.
Can you hear me, Professor?
I can, Andrew. How you doing?
Oh, man, I'm swamped. I've been studying like no other, trying to get ahead of everything so that way when it comes down to it, like I'll be able to segment my time out. So far it's been going pretty well. It's just been busting a lot of butt before that.
It's good. You just got to keep away from Daniela, right?
Exactly.
She's very needy.
I'm not going to comment.
Are you listening, Daniela?
Yes, I am.
Are you needy?
Yes, to be honest. But you can't say that.
We're all needy in our own special way. All of us. Ritvij, why you not got the camera on? Are you playing Gaming Hard on Rainbow Six?
He's trying to fix his Buzz Lightyear figure.
That's pretty funny. So I found out this morning, or actually last night, that Fullerton College is going to be remote for the fall. So I don't know when I'm going back to my office. I may not go back to my office till like March of next year. That's bad.
Oh, but do you know about Cal State Fullerton
No,
yet?
I don't know anything. They're not telling me anything. So for your sake, I hope that they don't go remote. I hope that they come back, but I wish I could tell you guys something, but I'm not in anybody's loop. I'm not important enough to get any kind of answers about anything, so just the way it is. Who else? Everybody, look like you guys are all here. Looks like, you know, people are doing well. So did everybody get their exam back and not someone else's? That's first question. I hope.
Yes.
I didn't get an email saying, "Oh my God, this is not my exam." All right. So we got that going for us. So we got today, and we got Thursday, and then the semester's pretty much over. We've got next week, Tuesday is really not an official class day. I will, like I mentioned earlier, I'll log in and I'll answer any and all questions you might have. And then Thursday of next week is the final exam, which, man, it's gone by fast. Very, very fast. Cedar, thank you for turning on your camera. It's good to see you.
Questions?
All right. Well, it looks like everyone's here. Why don't we go through the exam? Does that work for everybody?
We don't get internal.
Hey, what's up, Jorge?
Actually, I have a question from number 13.
I'm going to go through the whole exam, Minsung. So
Oh,
when you
okay.
get there,
Got
you want to ask? I figure it's probably easier if I just go through the whole exam. Actually, let me share the exam with my iPad.
There's no reason, actually.
So give me a
You don't
second.
know me, Jerry. What? I know you. You don't know me or your life. I mean my life.
Talk amongst yourself.
Nobody loves you.
Professor, I had a question about the final. Do you know what it'll be like looking like with multiple choice or like all open response?
Final exam is going to be multiple choice. It took me, I'm not complaining. I'm not whining or moaning, but it took me probably 12 hours to grade this exam. Normally, I would have an exam graded in like 2-3 hours. So instead of spending time carefully, I accidentally binged a whole series. A whole series of what, Cedar?
Dude, what's he doing?
All right, so that is what the plan is. The plan is going to be I'm here dogs barking, so I'm muting everybody.
Hello.
All right. So the plan is that the final exam will cover all the material from the beginning until now. And it will be multiple choice. I don't know how many it's going to be. But I think just for the sake of my sanity and perhaps yours, in terms of grading and getting things feedback back to you. Again, I don't write multiple choice questions to be like tricky or try to make your life complicated. But it was the Rapunzel's Tangled Adventure cartoon. Okay, yeah. So that's my plan. All right. If you got other thoughts on that, you can chime in via email or chat or something like that. Okay. Are there any other questions before I muted you all, so you have to unmute yourself if you have a question.
So the final, you're planning on making it all multiple choice?
Yes,
Is that what you said? Okay.
that is what I said. Is that a problem for you?
No. Bring it on, Professor. Whatever you got for me.
Yeah. All right.
And what % of our grade will it be?
Well, it'll probably be the same story. So if you look at the syllabus, I don't want to change the way things are written in terms of percentages, although I did already, right? Because I made the homework count for like homework and class participation. I believe that the exams were 20% and the final exam was 40%. Let me pull that back up because I
think you have it flipped. So like on the syllabus, it has
could be very well that I have it flipped.
examinations.
I'm pulling up the syllabus right now because that's what I'm doing. I don't have a great memory. The final exam is 20%. So you're right. I have dyslexia. The final exam is still 20%. Okay. So the other exams are 40%. The final exam is 20%. And then quizzes are 15 and the other 25 is homework. All right. And I am going to drop the lowest quiz score just like we said we would do. And normally I look at your final exam score, and if your final exam score, because it's cumulative, is substantially better than your exam score, means you learn the material. I've been known to substitute your final exam score for all your exams. So let's say that you're getting like a 75 on all your exams and you get an 85 on the final. I probably would give you an 85 for all your exams just because the exam is cumulative. And if you prove to me you learn the material, I would do that. I'm not putting it in the syllabus, but that's typically what I do. All right. So if you study hard and do really well on the final, it can make up for some bad exam in the first case. Does that make sense? Okay. Other questions? Other questions?
That would be only if you do better on the final than like.
Yeah, it's only if you do better, right? If you do worse on the final, it just counts for 20%. Yeah. It doesn't go the other way either. If you do worse on the final, it still counts. I'm not going to like get rid of it, right? So, but honestly, you guys are doing, I want to say for the most part, you're doing really well. And when you look through your exams, I didn't really see a lot of bad mistakes on this exam. I saw lots of little mistakes where you forgot to do some things. Almost nobody did resonance on ozone or the carbonate ion. A handful of you did it. I didn't take off a huge percentage for that, but stuff like that, some naming issues, some other things like that. So there will be things that you're going to have to practice if you want to do really well on the final. But honestly, I would think if you've been paying attention, if you've been doing the homework, you really don't have to cram for the final. I really don't think that that's going to be the case for this class because you've been having to keep up all along to do well on this exam, right? I mean, you need to know how to do stoichiometry. You had to do sig figs. You had to be able, well, some of you got dinged on sig figs too, right? You got to be able to do sig figs. You got to be able to do conversions. All that stuff was pretty much on this exam. There really wasn't a whole ton of things on this exam that weren't covered on the first couple of exams. So this exam 3 was kind of a good prep for the final exam, I think. Other questions?
And how many questions would it be on exam?
How many questions? Sammy, I don't know for sure. Somewhere probably between 50 and 100. I don't know. Yep, you'll have 2 hours to take the exam, right? And the time for the exam is different too, I believe. I don't think it's the standard time. I have to double check. Oh, it's right here. The final exam is from 5 to 6:50. So that's basically 5 to 7. So you'll have 2 hours to take the final exam. I would think, again, I'm not going to try to get 100 questions. I'm going to try to cover all the material and not be redundant and ask the same question multiple times. So when I write the exam, I'm going to go through all the topics we covered and try to write questions that cover all the topics we covered, right? Maybe sometimes I'll come from a couple different angles, right? With gas laws and things like that. It might look like it's the same question, but it'll be assessing slightly different things. So I would anticipate somewhere between 50 and 100 questions, right? Keep in mind, the more questions I ask, the less each question is worth, right? So if I only ask 50 questions, they're worth 2 points each. If I ask 100 questions, they're only worth 1 point each. So just, it is what it is, but I don't know because I haven't written it yet, Sammy. Sorry. May 14th from 5 to 7 p.m. That is correct, Chris. And it's not in MH 536 or 586 or whatever room we used to meet in. I don't even remember what the room number was that we met in. It's sad.
And Professor, how does
Yes.
it are you gonna send us like the exam and then we have to
Same story, same way. I'll post the exam or I'll email it to you 5 minutes, right, before we start it. And then I'm guessing because it's multiple choice, it probably would just be easiest for you to write your answers on a sheet of paper and then send me a picture of that sheet of paper, right? That would probably be the easiest. One thing I found is some of the stuff you guys sent me, if you got your exam back in like 3 or 4 PDFs, however you sent it to me, it was such a huge file. I could not get it to go to Notability or Noteworthy or whatever that thing's called in one file. I would send it and it would keep giving me errors. And I finally realized, oh my God, this is like a 25 megabyte file for one picture. So maybe you're taking like super high resolution pictures and it just makes a really, really big PDF. But that shouldn't be a problem for the last exam because it's just going to be an answer sheet. So you probably should be able to get by with one sheet of paper with the answers to your multiple choice questions. And that way then you don't have to print anything. You can just look at it on your screen. But I'm trying to minimize the complexity for you guys and me. Sammy, any more questions?
No, thank you.
Come on, Sammy. You always have one more question. No one else?
Professor, what time did you say the final was?
The final is based on the syllabus. It says it's from 5 to 6:50, but I'll give you from 5 to 7. Honestly, I'm going to give you 2 hours from when I start it. So we'll show up at 5. I'll start the Zoom meeting at 5, and then we'll go from there. Also, I realized just today, I was thinking that the material in Sapling is going to cover some questions like solutions and other things, which we're not going to get to. So I need to go in there and get rid of those questions in the homework. If I forget to do that, please somebody send me an email, or just somebody send me an email anyways to remind me. I'm going to write myself a note right now. Delete homework. To delete some of those questions, which will be on topics that I'm not going to cover. So today and Thursday, so once I go through the exam, I'm going to go into talking more about dot structures, shapes of molecules, and polarity. And then I'll probably be able to touch on intermolecular forces. You know, why is something a solid? Why is something a liquid? Why is something a gas? No way I'm going to get into solutions, right? So whatever we get done today and Thursday, that's it. And then next Tuesday, you'll be able to ask questions. And then Thursday's the exam. Hopefully that. Do you know when you'll have them deleted? Atri, I don't know. I just thought about it today. I'll probably do it tomorrow. I'll give it my best shot to get it done tomorrow. Okay? Thank you. You're welcome. All right. Okay, so let me see if I can share the exam with my iPad. Let's see, share, send a copy, do this, airdrop. My iPad, accept, notability, done. Let's see here. Doesn't look like it took it. Let me try this one more time. Send a copy. Airdrop. It must just be taking its time because it's a big file. I don't know. Let me try it a different way. Actually, yeah, it's best to have that up. Let me just send it to myself as an email. Sorry, guys. I should have had this done already. All right, let me try this. See if I can get this to work. And of course, that is not the one I wanted. Sorry. All right, that's the right one. Okay. All right, hopefully this will work this time. Since you just want an answer sheet for final, then you won't have partial credit. Well, because it's multiple choice and they're only going to be 1 point each, more than likely 1 to 2 points, I probably will not do partial credit on the final exam. However, I'd consider, if you got it back and you looked at it and you're like, here's what I meant on this, I'd give you a little bit of time to, just like you do on these other exams. Why is this not working? I thought I sent it to myself. I did. It's just taking its time. Taking its sweet old time. All right, well, that answers that. I'm not going to wait for this forever. I don't know why it's not coming to my mail. It's just being a pain. So let me just open a new note, and I'll just read the questions from my laptop, and I'll work on notability with you guys. All right, so let me share the screen. Okay, so you should be able to see my iPad now, and of course it's got all this other stuff in there. Life is just being complicated today. Who the heck did I send that to? Oh my gosh. Sorry. It looks like I sent that email to somebody who should not have gotten that email. This is what happens. We're almost there. All right. I'm going to try this one last time. I don't know if Notability is going to let me open it up. And there it is. Okay, it did. Oh, finally. Okay. I'm sorry that took so long. It's not let me make this any bigger. Probably not. Okay. So which of the following elements has the largest atomic radius? So if you're looking at the periodic table, right, and that's what you want to do. So you've got carbon, then below carbon is silicon, below silicon is germanium, and below germanium is tin, right? So you remember that radius increases as you go down, so tin is the correct answer. Which is the largest ionic radius? So you guys might have the ability to argue in terms of this question, because if you're looking at the periodic table, potassium is above rubidium, right? So rubidium is larger than potassium, so potassium is never the right answer. The question is, which is bigger, rubidium or rubidium plus? Well, if you take an electron away, which this is done, right? If this is the size of rubidium and you take an electron away, rubidium plus would be smaller. So the answer is rubidium. However, rubidium's not an ion. So you might be able to say, hey, Dr. Hartmann, the only two acceptable answers are potassium plus and rubidium plus, because those are the only two ions. And of the two, rubidium is bigger than potassium. So if you were thinking that legitimately, you could argue that that was the correct answer, and I'd have to give you that point back, okay? I apologize, that question was misleading.
So we would be getting that point back?
If you made that argument, right, if that was what you were thinking, if you were saying, what, I have to pick an ion, these are the only two that are ions, and this is the bigger ion, then semantically, definition-wise, rubidium plus is the biggest one, but the one that has the largest radius is rubidium. So there's your answer. If you got rubidium plus and I marked it wrong, and that's what you were thinking, then send me a message and I will give you credit for that. Okay, but don't send me a message yet, because you might have more things that I have to give you credit for. Okay.
So why isn't it rubidium plus? Because it does not have an ion?
Well, no. Why isn't it rubidium plus? The way I read the question was basically which one's the biggest, right? Which has the largest? This should have been which has the largest radius, right? That's how I meant it to be. Which one has the largest radius? And that ionic slipped in there. So officially, rubidium is the biggest of those species, but the largest radius, right, is rubidium plus. If you really want to get down to it, all right, rubidium has an ionic radius, even though it's not an ion, right? Because you could say, well, the rubidium has rubidium ion associated with it. So all around, it's a poorly worded question, and it's totally my fault. And so if you had either rubidium or rubidium plus, I will give you credit. You just have to ask back for that point. Okay. Which has the largest ionic radius? Now see here, these are all ions, okay? And so if you think, look again, fluorine, chlorine, bromine, and iodine, they go down in the periodic table. I don't know what the heck that is. That does not look like a fluorine.
Sorry, quick question. That question was worth 3 points?
Yeah, they should have been worth 3 points each. So did I say 2? You'll get your 3 points back. Okay? Yeah, all the multiple choice were 3 points each. So going down the periodic table, the atoms get bigger. These are all ions, right? Fluorine, chlorine, bromine, and iodine, F minus, Cl minus, Br minus, I minus. When you add an electron, so if this is the fluoride, the fluorine, F minus, I'm exaggerating, so if this is F, this is F minus. So they all get bigger than their corresponding atom. But as you go down, everybody gets bigger. So in this particular case, iodine is the largest of all of them, without a doubt. Okay, which has the lowest ionization energy? All right, so that's basically asking you which one is the biggest and has the smallest charge in the nucleus. So what I'm going to do when I look at these is I'm going to look at where they are in the periodic table. And if you think about it, these are all alkaline earth metals. So you've got beryllium, magnesium, calcium, and strontium, right? They sit like that in the periodic table. So which one has the lowest ionization energy? That's going to be the one that's the biggest, right? And doesn't hold on to its electrons the tightest. So strontium is the biggest, so it has the lowest ionization energy. There's other questions related to that too as well. I could say which one's the most reactive, and that question came up down here when we were talking about reacting something with chlorine, right? The bigger a metal is, the more reactive that metal is, right? So again, if you think about lithium, sodium, potassium, rubidium, cesium, francium in group 1, you know, sodium's pretty reactive, but potassium's way more reactive, and rubidium is even more reactive. So as you go down, they get bigger. Their goal is to get rid of an electron. It's easier to get rid of an electron when they're bigger, right? So they're all kind of related. And those are simple kinds of questions to think about on the final exam. When we're asking about periodic trends, we'll be looking at those sorts of things. Which has the highest electron affinity? Okay, this says which one really wants electrons, right? Which one wants electrons? A lot of you picked argon, all right? And I get why you picked argon, but argon's a noble gas. It doesn't want any electrons, so it has no electron affinity. It's full, it's happy. Chlorine is the right answer, right? Chlorine is 1 away from a full shell, right? And if it can get 1 electron, it really wants to get that 1 electron. Sulfur and phosphorus want to get electrons, but chlorine wants electrons the most. And again, how do you know that? Well, electron affinity is parallel to size. And here's fluorine. Chlorine is right here. Sulfur and phosphorus, right? Chlorine is the closest to fluorine. Fluorine is the biggest hog of electrons. Chlorine is right there. And you might say, well, isn't sulfur right close to it? It is, but chlorine is closer in terms of size and all those other things, right? These are all in that period, so they all have essentially the same number of energy levels. But remember, for the nonmetals, every time you go 1 over, you're adding an electron and a proton, and they're shrinking. They're getting smaller all the time. And so chlorine can get an electron really close to its nucleus, so it really wants electrons. Overall, the group with the lowest ionization energy on the periodic table, the group with the lowest ionization energy, that means which ones really like to give up electrons. So noble gases, nope, they want to hang on to their electrons. Halogens, they're right next to the noble gases. They don't want to give up electrons. Alkali metals or alkali earths? Well, alkali metals, right? So if you're looking at this, group 1 is alkali, group 2 is alkali earth, alkaline earths. These guys right here, right, are more reactive than these guys right here. So it's the alkali metals are the more reactive ones. which has the highest electronegativity? You could have looked these up on the table, or you could just remember the closer you get to fluorine, the more electronegative something is. And so sodium's a metal, he doesn't have a high electronegativity. Aluminum's a metal, he doesn't. Sulfur is a non-metal, it's got a pretty good electronegativity. But chlorine is way over here right by fluorine, same story. So chlorine has the highest desire for electrons in a bond. So that's what electronegativity is. Chlorine is the correct answer. What charge will oxygen have after it's gained a full shell? Well, remember, oxygen is in group 6. So it's got its p electrons, 1, 2, 3, 4, 5, and the s electrons are full. So it's got 6 electrons, right? 1, 2, 3, 4. It will, 1, 2, I put one too many dots in there, I think. I'm not sure. I think I have the eraser. Trying to get rid of that, all right? So 2, 4, 6, those are the 6 electrons for oxygen. And there's 7, there's 8. It's gonna get 2 electrons. So -2 is what it normally forms. Which electron reacts most quickly? I guess that might have been an understanding of, you know, what do you mean by most quickly? Which one is the most reactive, right? And again, that's similar to this question. It's not the same, but it's similar. So if you look at these, this is going across. So sodium, magnesium, aluminum, silicon, that's kind of going across the periodic table. They get more and more like non-metals, right? Sodium is a non-metal, or excuse me, chlorine is a non-metal, so it's really going to react with a metal. So in this case, sodium is the one that's the most metallic. It's farther to the left. So that is the correct answer. And which of these is the most reactive? Oh, that's the question I asked up right here. Lithium, as you go down within the alkaline earth metals, every step you take down, they get more and more reactive. So rubidium is the farthest down in that series. So he is the most reactive of those guys. Okay. Give the electron configuration and orbital notation for selenium. So if you go to a periodic table, so let's just pull up a periodic table. Oh, come on. Okay. Let me just pull up a periodic table. Oh, come on, give me a periodic table. Sorry, it's just not what I wanted. I just want a periodic table, people. Okay, there we go. Let me go back to stopping the share and let me share the other screen. Come on. So there's the periodic table. So if you look at this periodic table, you can see that we're talking about selenium, which is right here, right? I'm always going to use the noble gas core whenever I can. So the closest noble gas is argon. So that takes care of everything through 18 electrons. So if I were to go over here, 1, 2, 3, 4, then I'm going to have to start right here in 4s2. So let me go back to my iPad. Okay, so for selenium, it's going to be argon, 4s2, 3d10, 4p, and what did I say selenium was? Selenium's 1, 2, 3, 4 in. So 4p, 4. So that's the electron configuration. Some of you did some weird things with orbital notations. Remember, for orbitals, you got to make dashes for however many orbitals there are. So I'm going to write it down here. Actually, let me erase this, and I'll do it next to there. So orbital notation is going to be argon, 4s, 3D, oops, and then 4P. So 4s2, 3D, 3D10, 4P, 1, 2, 3, 4. So that's what it should look like for the electron configuration and the orbital notation. If you're going to go to the selenide ion, all right, so this made you think, what do you mean by selenide ion? We need the most common ion of selenium. And based on this, you can tell it only wants to gain 2 electrons. So the most common ion is selenium -2. There's a couple ways you can write this.
Can I have a quick question about those?
Sure.
So you said you asked for electron configuration and the orbital notation, but was it wrong for us to just put them together to save space right there in that area?
If I couldn't tell, I might have marked it wrong. So if you gave it to me and they're both there and you did this and I didn't notice it, yeah, let me know.
Well, I mean, yeah, because mine's pretty clear, and you crossed out my orbital notation.
Oh, I probably screwed up then. Yeah, just say an email to me and say, hey, dude, what the heck did you do that for? That was dumb. I'll give you the credit back.
Okay, thank you.
That was, it was a long day of grading exams. Anything could happen, right? So if you look at selenium on your periodic table, I'm not sharing my screen, but 2 elements after selenium is krypton. So you could, in fact, give that as the correct electron configuration. That's also the correct orbital notation, right? You don't have to do anything. That's the next noble gas. Or you can do this argon, this one right here, except it would be 4p6. I'm trying to see my screen again. Or it would be 4p6. So this right here would be 4p6 for the ion, and this would just be full for the ion, right? So you could still start with argon and make this full with all electrons. Start here with argon and make that full, so 4p6. Or you could just write Kr brackets -2. It's the same thing. Okay. Give the correct Lewis dot structure for the following. So ozone, O3, so you've got 6 times 3 is 18 electrons. Make one of them the central one. I've used 2, 4. So 18, I've got 14 electrons, which is 7 pairs. 1, 2, 1, 2, 3, 4, 5, 6, 7. So that's the dot structure for ozone. Not everybody's happy, so I got to add a multiple bond, but do I make the multiple bond here or here? The answer is yes. You got to make them both. So you needed to show resonance on that particular structure. And so it would have looked something like this. O, double bond, O, single. Now, you know what? Let me erase some of this mess. All right. So the correct structure would have been O, single bond O, double bond O, lone pair. Excuse me, not lone pair. Lone pair here, lone pair here, lone pair there, and then this in resonance with this guy. So that was resonance. If you didn't draw resonance, then you lost half a point. No big deal, but you should be aware that that's existing. For ammonia, nitrogen's got 5 plus 3 from the hydrogens is 8 electrons.
Quick question again.
Yep.
For ozone, you need 2 electrons in the middle, right?
Pardon? Oh, sorry, I left those out. Yes, sir, indeed. They are still there. Good catch. And these are here. It's hard to draw. My stylus is really touchy. Boron tribromide. So that's boron, which is in group 3. 7 times 3 is 21. I have 24 electrons. So each of the bromines gets a full valence shell. And that's really it. I know you might be tempted to put a double bond in there to make everybody happy, but remember boron and hydrogen and beryllium, those guys are happy with a small set. They're the only ones that are happy with less than 8. Carbonate ion, if you remember, is CO3 minus 2, so this is charged, so we're gonna have to put it in brackets. And if you draw it, what you're gonna end up with, the only way to make it happy is to have a double bond somewhere. All right, and of course the double bond is here. It could be in any of those positions. So I'm not going to put the lone pairs in just because I'm lazy. That's the same as the double bond here, here, right? And then you have to have the charge outside those brackets, right? So the lone pairs still need to be on there. Well, maybe I'll put them in. Let me just pick a thicker pencil. Might be easier to do. All right, so pay attention if you have identical places to put the multiple bond, not a single bond. Some of you did resonance with single bonds, now just with multiple bonds. Silicon tetrachloride, so silicon SiCl4, silicon's got 4, 7 times 4 is 28, so you have 32 electrons to put in. That's going to make me happy. Oops, that's not making me happy. Silicon. Let me do some erasing here. So that, and then phosphorus. So phosphorus is, I'm pretty sure phosphorus is in group 5, same family as nitrogen. So phosphorus has 5 triiodide, so 7 times 3 is 21, so that has 26 electrons, right? Pi3. So put the phosphorus in the middle, iodines around it, give each iodine 8. 8 times 3 is 24, 25, 26, so you put the remaining 2 electrons on the phosphorus, and that makes everybody happy. Okay. You are planning a trip from Cal State Fullerton to Death Valley. If the pressure in your tires is 35 psi when you leave Fullerton and the temperature is 72, when you get to Death Valley, the temperature is 122. What will the pressure in your tires be at this temperature? Okay. I typically just remember this expression, P1 V1 over T1 equals P2 V2 over T2. All right. I'm not interested in volume, so the volume just goes away. So it's P1 over T1 equals P2 over T2. Whenever we're dealing with temperature, you have to be in absolute temperature. Right? We didn't really talk much about the Fahrenheit absolute temperature scale. So what you got to do is you got to change these temperatures to Celsius and then convert them to Kelvin, right? And again, this was a take-home, basically a take-home exam. So you could have used your calculator if it has a conversion button. You could have used Google to convert the temperature, or you could actually have done the conversion like we learned how to do the conversion, right? And so I'm looking at my notes because I don't remember this. 72 degrees Fahrenheit is 22 degrees Celsius. So 72 degrees Fahrenheit, that's 22 degrees C. And let's see, 122 is 50 degrees C. Right, so the way I did this problem is I said pressure 1 is 35 PSI. You can leave it in PSI, right? Temperature is really the only one you have to convert. As long as you're in the same units for all the other stuff, those units work, right? Because all the other units have a 0 that means 0. 0 PSI means no pressure at all. 0 Celsius, does not mean no temperature, right? 0 liters, 0 milliliters, right? Any of those units where 0 means 0, you can use them straight up in these equations where you're just changing ratios. If you're using the ideal gas law, though, remember, R has units, so you have to have the right units for that. So 35 psi equals P2. And let's see here. If I want to get P2 by itself, then a T2 comes on the top and T1 is on the bottom. So T2 would be 50 plus 273. And this is 22 plus 273. And if you do the math, it comes out to, I think, 38 psi. Your answer really should only had 2 significant figures because everything I gave you only had 2 sig figs. I only took off for sig figs if you were off by more than 1 or 2, right? So if you had like 37.9 or even 37.95, I looked the other way. But if you had a whole string of digits, like on this next question, a lot of you had like 139,385, right? I can't let that slide. That's way too many sig figs.
Professor?
Yeah.
So every time you use a standard temperature, it's always going to be in Kelvin, correct?
Well, no, standard temperature. So STP is, right, 0 degrees Celsius and 1 ATM. Anything else that's equivalent to that works too. So 0 degrees Celsius is the same thing as 273, right? So you could use either of those. It doesn't matter. 1 atmosphere is the same as 760. It's the same as 101 times 10 to the 5th kilopascals. Whatever units you want, as long as they correspond to that same value, right? When we're doing ratios like this with P1, V1, and T1, as long as R is not in the expression, right, you can pick the units for everything except temperature, right? When T is in here, you have to be in an absolute temperature, and the only absolute scale we used was Kelvin. There is an absolute scale for Fahrenheit. It's called the Rankine, R-A-N-K-I-N-E, but we never used it, and I don't want to bother you with it. But if you had used it, I'd give you credit. It's not a problem. Right? So temperature always has to be absolute. Pressure and volume can be any units as long as they're the same units before and after. It'll work. Okay, a weather balloon has a volume of 6,450 liters at sea level, and I'm telling you that that's the pressure and that's the temperature. What new volume will it occupy at 20,000 meters where the temperature is minus 58? Now, I just made these numbers up. This should probably be more like 20,000 feet, not 20,000 meters. 20,000 meters is probably outside the atmosphere, but whatever. The idea is as you go up, the atmospheric pressure goes down and the temperature goes down. And so that weather balloon should get really, really big, which in fact it did, right? So this is P1 V1 over T1 equals P2 V2 over T2. And we want to know the new volume, right? So that gives us P1 V1 over T1. And then I have to invert this and bring it to the other side. So that's going to be T2 over P2, right? And that's going to equal V2. So all you got to do is just plug these particular numbers in, starting with volume 1. So I have 6,450 liters. And I'm going to do P1 over P2. So P1 is 750. P2 is 25. T2 is minus 58, so that's 273 minus 58. That's in Kelvin. And then this is 273 plus 25, right? Minus 58, it's plus a minus 58, right? So that's Kelvin. And if you do the math, without rounding, you get 139,605, something like that. And then if you look at this, this is only 2 sig figs. So your answer really can only have 2 sig figs. So 140 or 1.4 times 10 to the fifth. And then we were talking about volume, so this is liters. Okay. So not a super complicated problem, but a problem nonetheless. And again, you will be dealing with questions like this on the final. It will just be, I'm going to give you 4 choices of answers, and you'll just have to do the math and pick the answer that best matches the math. So you're still going to have to do these kinds of questions. You're still going to have to do calculations, but the answers will be there for you to select from. And I will, I'll pick answers that I know are common mistakes because, that's how you do it. Not like I'm trying to trick you, but that's the bane of multiple choice, right? How many grams of oxygen are contained in a cylinder that has a volume of this at STP? So this is the PV equals nRT. N equals PV over RT. Remember, N is going to be in moles, so then you have to change it to grams using the molar mass. So in this particular case, let's see. We're at STP, so we know what the pressure and the volume is. Pressure at STP is 1 atmosphere. They gave us a volume of 0.855 liters. I'm just doing that math in my head. R is still 0.08206 liter atmospheres mole K. And temperature is 0 degrees, so it's 273 K. So if you solve this, go ahead and solve it on your calculator, you will get 0.0381 moles of oxygen. You just need to remember that 1 mole of oxygen is 32 grams of oxygen. And then if you do the math, you should get something like 1.22 grams of O2. Some of you forgot to change that. You made this 16. I think I took a point off for that. Some of you had a little difficulty with the algebra here, rearranging that expression. I usually only take 1 point off for math errors like that. So it's, again, you want to practice. You want to get good at this. But this is really a chemistry class, and I'm trying not to punish you for making math errors, although you really should be careful about your math and those sorts of things. So on this one, I was kind of hoping that you would complete this equation in words, but I guess I didn't make that clear enough. So as long as you completed it in some fashion, I was fine with that. Aqueous calcium nitrate plus aqueous aluminum phosphate yields aqueous aluminum nitrate plus solid calcium phosphate. And I did it this way so that you wouldn't have to worry about writing the formulas first. All right, I just wanted you to kind of get it in words. But now for the molecular equation, you actually got to write these out, right? So you got to remember calcium is +2, nitrate is -1. So this is CaNO3 AQ plus aluminum phosphate. Aluminum is +3, phosphate's -3. So AlPO4 aqueous goes to aqueous aluminum nitrate, AlNO3 AQ plus solid calcium phosphate. So plus Ca3PO4 to solid, right? Then you got to balance it. So this is a little more complicated. You need a 3 for the calcium because there's 3 over here. 3 times 2, you got 6 nitrates. You got, well, 3, you need a 2 over here, you need a 2 over here, and that should balance everything. So I got 3 calciums, 6 nitrates, 2 aluminums, 2 phosphates, 2 phosphates. So it's balanced. Ionic, you got to break apart everything that's aqueous into the correct number of ions. So calcium nitrate, there's 3 of them, so I get 3 Ca plus 2 aqueous. I'm going to go to a slightly finer pen because this is going to make a mess. Plus, I've got 6 NO3 minus aqueous plus 2 Al plus 3 aqueous plus 2 PO4 minus 3 aqueous. That's part of the previous question. Goes to 2 Al plus 3 aqueous plus 6 NO3 minus aqueous plus Ca3 PO4 to solid. It's solid, so it don't have to break apart. And then, of course, to get the net ionic, you cancel out everything that's the same on that side. Oops, that's not the same. 6 nitrates here, 6 nitrates there, 2 aluminums here, 2 aluminums here. So what I'm left with is 3 Ca plus 2 Aq plus 2 PO4 minus 3 Aq goes to Ca3 PO4 to solid. So that's the net ionic equation for that guy. Last question. And again, you can kind of see how I asked you a bunch of questions with this one. I'm going to ask you to do stoichiometry, but I gave you a word equation and I didn't balance it. So that's the first thing you're going to have to think about. You're making methanol by reacting hydrogen gas with carbon monoxide. So you need to write H2 gas plus CO gas produces CH3OH. I didn't tell you what the state on that was, so you didn't have to do it. Actually, I didn't even tell you that this was a gas, so you can't put that there. At the conditions this reaction runs, everything's a gas. So, I mean, you could have put a gas there anyways. If you didn't have this little G, I didn't take off for that. I wasn't really paying attention to that. I was mostly looking, did you get this as H2? Did you write this as CO? Did you balance it, right? So there's 4 hydrogens on this side, so you need a 2 there, a 1 there, and a 1. So it's pretty simple to balance. A number of you balanced it and then never used that balanced equation. That's problematic. The reason you write a balanced equation is so you can use that balanced equation. Okay, this is an excess limiting, so I'm giving you grams of this and liters of that. So what you have to do anytime you have excess limiting is start with each starting material and determine how much product is formed. So 2.5 grams of H2, 1 mole of H2 is 2.00 grams of H2. I wasn't super picky about the actual molar mass of H2 you use because it depends on the periodic table you use, right? So because I'm not supplying you with a table, I'm not going to be super picky on that. I'll give you a little more leeway as long as it's close. Balanced equation says 2 moles of H2 for every 1 mole of CH3OH, and then 1 mole of CH3OH. So carbon is 12, plus 3 is 15, plus 1 is 16, plus 16 is 32. So this is basically 32.00 grams of CH3OH. So if you go through and do all this math, you should end up with, so I want to say 20 grams. I graded this, looked at this question 100 times or 40 times. I should have it remembered. This comes out to 20.0 grams of CH3OH. Then if you start with 30 liters of carbon monoxide, 30.0 liters of CO, it's at STP, so you can say 1 mole of CO is 22.4 liters of CO. This is only at STP, all right? I want you to be careful. You can't use that relationship if you're not at STP. 1 mole of CO for every 1 mole of CH3OH. And then 1 mole of CH3OH is still 32.0 grams of CH3OH. You go ahead and do that math, you're going to end up with 42.86 grams of CH3OH. Now, a bunch of you did that you got this number and you got that number, and then you just stopped. You didn't give me which one of those is real, right? So make sure, well, on the final, it's going to be multiple choice. You're going to have to pick an answer, right? But this is the smaller number, so that's the answer to this question. How many grams of methanol can be produced? The answer is 20, okay? I would say probably 5 to 10 of you had both of these numbers and you didn't pick one. You just left that information for me to guess. Don't do that, all right? You got to tell me which one's the answer, especially on an excess limiting. I didn't take off a lot if you did that, but I couldn't just let it slide and not take something off, okay? Because this is the right one, then H2 is limiting, all right? So that's the next one. You had to somehow tell me that hydrogen was limiting. And then the last question is, how much of the excess remains when the reaction's complete? Now, I gave you this in liters. So it would seem legitimate that you would tell me how many liters are left over. Some of you decided to give me grams. That's fine, all right? The only way to do this question is to start with this and see how much of this you need, all right? So 2.5 grams of hydrogen. There's 2.00 grams of hydrogen for every 1 mole of hydrogen. The balanced equation says you have 2 moles of hydrogen for every 1 mole of CO. And 1 mole of CO is 22.4 liters of CO. If you do this, you're going to get a number. You're going to get 14 liters of CO. That's 14 liters of CO needed to react with 2.5 grams of H2. You were given 30.0 liters of CO. If you used 14.0 liters of CO, that means you have 16.0 liters of CO excess. There are other ways to do this, and probably 3 or 4 of you figured out other ways to do this problem, and I gave you credit for where you did correct work, and I took a little bit off for when you did incorrect work. A lot of you had really good ideas. You got a lot of this done. And again, I realize this is an exam you're taking at home and you have access to the internet and have all those things. And I was hoping that you would not look up answers, and I don't feel like any of you did that. But that's the world we live in, right? So most of you did really well on the exam. I seem to feel like you're doing about the same as you have for all your other exams. You might disagree. Maybe you're doing better, maybe you're doing worse. But okay, so here's the deal. If you feel like you deserve more points on any of these questions, based on the answers I've given here, just send me an email, say, hey, on this question, here's what I did, here's what I think I deserve more, you took off this, or I can't tell what you did. I tried to write legibly, but I'm not always that good. Nick, you got a question?
Yeah, Professor. For problem 14, what do you mean by absolute temperature? Because
Okay, problem 14, an absolute temperature is a temperature where 0 corresponds to 0 molecular motion. So
it can be 72 Kelvin.
Pardon? It has, yeah, Kelvin and Rankine are the only absolute temperature scales. You use Fahrenheit as I gave you, and the problem with using Fahrenheit is 0 degrees Fahrenheit is not 0 molecular motion. You have to always be in an absolute scale when you use temperature.
Oh, I totally slipped up. Thank you, Professor.
Yeah, no problem. I don't think I took a lot off.
Yeah. Thank you.
You did really well, if I remember anyways, Nick. You should give yourself a pat on the back.
Thank you, sir.
All right. Okay, I'm going to stop sharing my iPad here. No, I don't want to do that. Zoom. I'm not sure what's going on, why I'm just having a hard time. Oh, here it is. Stop share. All right, let me look at your smiling faces and avatars. Smiling face. Hey, Minsung, it's you and me again. Everyone else has got their avatars up. Since you should, LOL, gone to the wind. Okay, any other questions about, who's this? Jorge, you changed your Changed your picture. Any other questions about the exam? No other questions about the exam. Okay. Well, that was easy. All right. So what I want to do next is I want to progress a little more in depth, actually, into dot structures. So I'm just going to go here and change this. And then I'm going to share my screen again. All right. Okay, so there's my screen being shared again. Okay. I'm not sure what just happened there. Give me a sec. I'm just like totally screwing things up here. All right. Okay. So let's say we have a dot structure. Let's pick a simple one. CH4. Okay, so that's be the dot structure that you would have drawn. So the question is, what does this look like in real life, right? On the picture, it looks like a flat molecule where this is 90 degrees, this is 90 degrees, this is 90 degrees, and this is 90 degrees. Right? And the reason for that is I'm trying to draw a structure that has some three-dimensionality, right, in the flat plane of the page. Right? So how do I get around that? Well, the way we get around that is we start to talk about something called molecular geometry. All right. What I'm going to introduce to you is something called VSEPR. Right? This stands for valence, oh my gosh, valence shell electron repulsion theory. And basically what it's saying is that electrons that are paired up in the valence shell, now remember, valence is the outermost energy level. And if you think about the periodic table, it's always going to be S and P. And if you think about what that means, is we're always going to be talking about at most 8 electrons or 4 pairs, right? So this right here is the valence shell. These are the electrons. They're in pairs, and they hate each other. They like to repel from one another. So the question is, what shape do I get if I connect those electrons but try to get them to repel from one another? All right? Well, instead of making you think about it, I'm just going to kind of throw it out there. So if I have a nucleus and I have 4 sets of electron pairs, so electrons like to stay together in pairs. When I drew CH4, right, I just had them in that particular plane, and it looked like they were 90 degrees apart. But in reality, that's a 2-dimensional picture. If I were to do this in 3 dimensions, all right, what I'm going to find, and the way I'm going to be able to show this to you, is to introduce something called a wedge and dot model. All right. So what I'm going to show for you is, what I'm going to try to do here is draw this in a 3-dimensional fashion. I'll put these electron pairs here. All right. Okay. So if you can kind of get a visualization for what this is telling you, this line is really sitting on the plane of the page. This line is really sitting in the plane of the page. This wedgy thing is kind of coming out at you, and this wedgy thing is kind of going back into the plane of the page. Right? If your eyeball was up here and you were looking straight down at it, it would look like this. you'd be looking down this bond and you would see these guys. Oh, that's a bad picture. Let me try that again. You would see those 3 electron pairs, all right, spread apart, okay? If you rotate it along this axis, right, so if you grab this, it looks kind of like a top. You could rotate it along that axis and you could just spin it, and these guys are all perfectly symmetrical. They would just kind of change into one another, all right? This shape, if I were to put faces on it, all right, looks something like this. Right? Again, it's hard to draw. Looks something like that. So if you counted, you'd have this back face here, this front face here, and the bottom. It has 4 faces. Anybody know what a 3-dimensional object with 4 identical faces is called? You geometers out there? A regular
Tetra.
Something, something. I think I heard it.
Tetra.
Tetrahedron, absolutely. So the most common shape that we encounter for a central atom having 4 bonds to it is called a regular tetrahedron, or we just call it tetrahedral, okay? So let me just pick some generic species X. Right? We call this shape tetrahedral. These bond angles are all identical. They're all 109.5. Whether you care, great. If you don't, it doesn't matter. This is a result of nature. Nature wants to get these electron pairs as far away from each other as possible. And it turns out that in 3 dimensions, the way you get 4 things as far away from each other as possible is a tetrahedron. And the shape, right? So the shape is called a tetrahedron. The description of the molecular geometry is called tetrahedral. Okay? So when you have a molecule like CH4, this is a much better representation of the real shape. Right? It's tetrahedral. Okay? All the bond angles are equivalent. They're all between any 2 species. They're all 109.5. And there are lots and lots and lots of dot structures that have the shape tetrahedral, right? So you might remember, like on the exam, SiCl4, right? If we drew the dot structure for that, here's what you ended up with. So if I asked you to draw the dot structure for silicon tetrachloride, this is what you would end up with. If I ask you for the molecular shape or the molecular geometry, you would say tetrahedral. Boom, super easy. If I asked you for the bond angle, you would say, oh, it's 109.5. Boom, that was easy, right? Why we care about these things is going to come up in a minute. At this point, it's just something else for you to learn, right? But anytime you have a central atom with 4 identical things around it, the shape's going to be tetrahedral. The bond angle is going to be the same, right? Now notice what I said, a central atom with 4 identical things around it. If you put different things around, as you can imagine, stuff starts to change and you gotta tweak the picture a little bit, okay? This is just an example. What I'm going to describe for you next is the model system that we use to talk about shapes, right, and how we deal with it. But I got to define a few things for you, okay? So this is the central atom. We always knew that. This is a bonding pair of electrons, right? This picture doesn't have any lone pairs, so let me pick another one that you did on the exam, PBr3. when you finish the drawing for phosphorus tribromide, here's what you ended up with. Okay? So I might ask you this question. The central atom. Okay? What do you notice about the central atom? How many things, and I'm using generic term here, how many things does it have around it? Well, it's got 3 atoms, okay? But it has 4 electron pairs. And some of those electron pairs are bonding pairs, and some of those electron pairs are lone pairs. So life now becomes a little bit more complicated when you start to talk about this. So if we look at the previous screen, there's this thing called molecular shape or geometry. All right, so let's just ask for a second. Do you think the shape of phosphorus tribromide is the same as the shape of silicon tetrachloride? Just the molecular geometry. Do you think they have the same molecular geometry? Easy question. Yes or no?
No.
No, I agree with you. They do not, because this thing has 4 around 1. This only has 3 around 1. Okay, so what gives? Well, what gives is you got to start asking another question, right? So instead of just asking how many things you have stuck to the central atom, you have to ask this question. And this is, I'm going to throw it out there and we're just going to have to hash through it. How many regions of electron density on a central atom? Oh my gosh, what the heck do you mean by this? Regions of electron density. What I mean by that are these things, regions of electron density. You might say, well, aren't those pairs of electrons? Funny you should ask that. Let's look at another dot structure. How about we look at the dot structure for carbon dioxide? If you drew the dot structure for carbon dioxide, here's what you end up with, okay? That's the dot structure for carbon dioxide. Boom, that just happened. I drew that. You don't even have to worry about it. Does carbon dioxide have resonance? Easy question, yes or no?
No.
No, very good. Okay, so now ask yourself this question. How many regions of electron density are on carbon? So how many regions?
It's either 2 or 4.
Yeah, absolutely, Cindy, you're right. It's either 2 or 4. What are you going to go with?
2.
Yes, that is the correct answer. There are 2 regions of electron density. And you might say, well, wait a minute. Isn't that really this? Isn't that a double bond? Isn't that 4 electrons? Yep. That's why I talk about regions of electron density, not electron pairs. And there's formulas to remember. There's all sorts of complicated things. It just makes life complicated, right? If you look at a structure and say, okay, I don't care if it's a single bond, a double bond, or a triple bond, I'm going to count this as a region of electron density. I'm going to count this as a region of electron density. You will not go astray, okay? So this carbon has 2 regions of electron density. So that's a question you're going to have to ask yourself when you start to talk about shapes, okay? So what I'm going to propose for you now is, well, actually I'm going to spill the beans on all the potential shapes that you have to consider, but we're going to start with the most common one first, all right? So we're going to start with regions of electron density on the central atom. And then what do you suppose is going to change the particular shape? Well, look at here. This central atom has 1, 2, 3, 4 regions, and it's tetrahedral. This guy's got 1, 2, 3, 4 regions, and it's not tetrahedral. We didn't decide what its shape is, but it's not tetrahedral. So how is PBr3 different than SiCl4? Okay, I know they're different atoms, but in terms of the regions, here's 4 regions, and every one of these regions has an atom on it. Here's 4 regions, but one of them is a lone pair. So this is actually the key to figuring this out. So what you got to do is you got to count up the regions of electron density and then number of lone pairs on the central atom, the Ca. Central atom is Ca. Okay, so we could have 4 regions of electron density and we could have no lone pairs. We could have 4 regions of electron density and have 1 lone pair. We could have 4 regions of electron density and we could have 2 lone pairs. We could have 4 regions of electron density, have 3 lone pairs. Can we have this, 4 regions of electron density and 4 lone pairs? Is this a possibility?
No, because won't all of them be bonded?
Yeah, it won't be anything. It'll just be a central atom with nothing bonded, right? So this is not a possibility. Okay, I'm going to turn my iPad sideways because I'm amazing and that's what I can do. It's not going to give me any more room, is it? Okay, I'm not going to turn my iPad sideways. It's not giving me any more room. Let me copy this because I want to, oh, that's not what I wanted to do. Is it going to copy or what? Where do I get the, here we go. Oh, look at that, copy. Did I copy it? All right. So, paste. And let me shrink this down to size a little bit. Oh. Whoa. All right, we don't want to do that. There we go. I want to shrink that down. All right, look at that. Done. Okay. And then what I want to do is I want to turn my pen on. I'm going to add 2 new columns. What I'm going to call is the electron pair geometry. And then I'm going to talk about the molecular geometry. Okay. I just threw this term out here, electron pair geometry. We already saw molecular geometry. So let's go back here. Silicon tetrachloride, it's got 4 electron pairs and all of them are occupied. So the molecule is tetrahedral. What if these chlorines weren't here? It would just look like this. What would the geometry of these electron pairs be? It would still be tetrahedral. There's 4 of them, right? It's still tetrahedral, no problem. So if you have 4 regions and none of them are lone pairs, the electron pair geometry is tetrahedral. Oh man, I can't even write. I'm going to have to go to a slightly finer marker. And the molecule is also tetrahedral. You might say, well, that's dumb. Okay, but let's look at the next one. I got 4 regions of electron density. That means the electron geometry is tetrahedral. Anytime you have 4 regions of electron density, the electrons are always tetrahedral. Okay. What changes, though, is what does the actual molecule look like? In the case of phosphorus tribromide, it's not a tetrahedron anymore. Let's sketch that, what that might look like. I've got a phosphorus I've got a lone pair up here. I've got a bromine down here. I've got a bromine coming out at me, and I've got a bromine going in the back. When I look at this molecule, do you think I see this lone pair of electrons? What do you think? Yes or no? See. No, I don't see them. All I see is the atoms. I see a phosphorus and 3 bromines. Does that look like a tetrahedron?
No.
But it looks like a subset of a tetrahedron, doesn't it? It kind of looks like a pyramid, which is in fact what that shape is. So if you have 4 regions of electron density and one of them is a lone pair, the molecule is actually what we call, I got to get this right, it's called trigonal pyramidal. That's a mouthful. Trigonal pyramidal. Right? I also want to take you, actually I won't take you, I'll just draw it right here. Lone pair, phosphorus, bromine, 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 right? Normally, this bond angle was 109.5, right? That's what it used to be. What are the odds it's still going to be 109.5? The fact that I'm bringing it up means no, right? So, easy question. It's either this or this, not a number. I'm not asking for a number. What's the new bond angle going to be? If it's not 109.5, it's either or. Come on, somebody take a stab. It's either something or something. Bigger or smaller. What do you think?
Bigger?
Smaller.
Yes, I got both answers. Woohoo! Well, let me explain to you what happens in the real world and then see if you can come up with an answer. So normally, these electrons are held on tightly by both of these atoms, and they spend a bunch of time hanging around the nuclei of those atoms. This pair of electrons only hangs around the phosphorus atom. So which of those do you think takes up more space? Which one has more free time to be where it wants to be? The lone pair or the bonded pair?
The lone pairs?
Yep, the lone pair has more time to be its own thing, so these guys take up more space. If this takes up more space, what happens to this bond angle?
Get smaller?
Yep, it shrinks. So lone pairs squash the bond angle. They make the rest of the bond angle smaller, all right? So this bond angle in the trigonal pyramidal is not 109.5. Is that a number you're going to want to memorize, what it really is?
No.
No. You're just going to need to know it's less than 109.5. Okay? You need to know it's less, and you need to know why it's less. I don't care if you memorize the number 107, something like that, 107.5. The actual number to me is not important. What's important is you know that when you have a lone pair, it squashes the molecule and the bond angle changes. Okay? What about this guy? Can anybody think of like the most common molecule where you have 4 regions of electron density in a central atom and 2 lone pairs? You've seen this molecule a billion times. The most common example.
H2O.
Yep, you nailed it, Min-Sung. H2O, let me not use red. So here's the dot structure for water. And again, you're used to drawing it like this. No problem. That's one way to draw the dot structure for water. What just happened? Are you guys okay? Something just went. You out there? You guys hear me? Min-Sung. Min-Sung.